session we will be seeing what are the deductions you can get from kinetic theory of gases. We have seen kinetic theory of gases, and from that we are going to deduct many deductions like Charles law, Boyle's law, kinetic energy, root mean square velocity, all these derivations from kinetic gas equation. So, here these are the name of the deductions, that is deduction from kinetic theory of gases, Boyle's law, Charles law, and RMS, root mean square velocity, and kinetic energy of gas molecules. So, these are the deductions we will be deriving from kinetic theory of gases, that is from that equation. Okay. Now, we all know that its kinetic gas equation, which is based on kinetic theory of gases, is as follows, that is P V equals 1 by 3 m n u square, n is a capital N, where P stands for the pressure, V stands for volume of the gas, m stands for mass of one molecule, n is total number of molecules in the gas, and u is the mean square velocity. It is the mean of squares of velocity taken, u square. So, this is the kinetic gas equation, and we are going to take deductions from this. So, first one what we are going to deduct is the Boyle's law. According to Boyle's law, we all know that when temperature is fixed and number of moles or mass, instead you can put it as number of moles fixed. Pressure of a gas is inversely proportional to its volume, or you can put it as P V will be a constant. This is what we have seen in Boyle's law. Now, how we will arrive at that? We know that kinetic energy of a gas is proportional to its absolute temperature, that is the average kinetic energy is proportional to temperature, that is the absolute temperature. Okay. Now, kinetic energy I am going to express as half m is the mass of a molecule and u square, we are using the mean square velocity instead of velocity. So, m u square proportional to T. For a definite mass, this is for one molecule, if the mass of the gas contains n molecules, the equation takes the form 1 by 2 into n. This is the number of molecules multiplied by m u square proportional to T. Now, here we have the expression 1 by 2 n m u square proportional to T, where we do not have anything related to the kinetic gas equation. So, now what we are going to do is, we know that kinetic gas equation is P V is equal to 1 by 3 m n u square. Now, here we are having it as 1 by 2. Now, I have to convert that in terms of 1 by 3 m n u square, then I can equate that as P V. But now, how we will do that? First, we are going to remove the proportionality, 1 by 2 n m u square is equal to a proportionality constant k into T, where k is the proportionality constant. Okay. So, 1 by 2 n m u square is equal to k T. Now, here I need 1 by 3. and I do not need this 2. In denominator I need a 3, okay, and I do not need this 2. So, what I am going to do is I am going to multiply both sides with 2 by 3. So, this 2 will get cancelled and the 3 will come over here. So, both sides I am going to multiply it with 2 by 3. So, 2 by 3 into 1 by 2 n m u square will be equal to 2 by 3 into k t. So, both sides I have multiplied, it makes no difference. Now, what I am going to do is you can cancel this 2 with this 2, and this side on the left hand side what is left will be 1 by 3 n m u square is equal to 2 by 3 k into t. Now, you can compare that with the kinetic gas equation. So, this is a kinetic gas equation in which 1 by 3 n m n u square is equal to p v. Okay. So, this term I can replace as p v. Now, we can reach to the Boyle's equation, that is p v is equal to 2 by 3 k into t. K is a constant. Now, for Boyle's law we have the conditions temperature is constant and mass is constant or number of moles is constant. Now, considering that here in this expression what we have is the temperature, pressure and volume. Now, what we are going to do is this temperature is constant. Then P v will be equal to a constant. Why? 2 by 3 numerical is constant, k is another constant, and here temperature is maintained constant means the whole on the right hand side becomes a constant. So, I can put it as P v is equal to a constant, which is the Boyle's law. So, please note, see, we have started with kinetic energy proportional to absolute temperature. Substituting by kinetic energy, we are getting 1 by 2 mu square proportional to T, and for n moles multiplying it with n, you get as proportional to T. I am going to remove the proportionality and making as an equation introducing K, which is the proportionality constant. Okay. Now, what we have to do is we want any one of the side to be 1 by 3 m n u square, which is from the kinetic energy. If you get that, I can substitute that with P v, so that we have the terms involved in Boyle's law. Okay. So, for that what I am going to do is I am going to multiply both sides of the equation with 2 by 3. So, multiplying with 2 by 3, I will get it as 2 by 3 into 1 by 2 in n m u square is equal to 2 by 3 into k into t. Cancelling 2 on denominator and numerator, we get 1 by 3 n m u square is equal to 2 by 3. Okay. This is the substitution I am going to make, because from kinetic gas equation P v is equal to 1 by 3 m n u square, and 1 by 3 m n u square has been substituted by P v, and that is from kinetic gas equation. We get the equation modified as P v is equal to 2 by 3 k t. At constant temperature, the variable temperature becomes constant, and therefore, all the terms on the right hand side, that is 2 by 3 is already a constant, k is a constant. Now, t also becomes constant, or you can put it as P v is a constant, P v equals constant, which is Boyle's law, or you can also express it as P proportional to 1 by v, removing the constant. Okay. That is for Boyle's law. Now, let us see how we can prove it with Charles' law. Now, here all these derivations has to be done, and you should get the expression P v is equal to 2 by 3 k T. Now, with that, if you are asked Charles' law, you will have to start from, that is kinetic energy, average kinetic energy proportional to absolute temperature, derive, you reach this equation, that is P v is equal to 2 by 3 k T. Now, as it is done already, I am taking that P v is equal to 2 by 3 k T. Okay. Now, for Charles' law, what should be the condition? V is directly proportional to T, or the other way to express is V by T is a constant. The condition is pressure is constant and number of moles. These two are pressure and number of moles are constant, or mass is constant. Now, we have got an expression P v is equal to 2 by 3 k T. Now, we want in terms of volume. So, I can put V is equal to, I am taking pressure to this side, you will get 2 by 3 pressure, it comes to the denominator pressure, okay, into K into T. So, the expression takes the form like this. Now, the condition for Charles' law is pressure is constant. Once the pressure is constant, this will be 2 by 3 is already a constant, P is constant, K is constant. The only variable here is the temperature. So, temperature is the only variable, and you can say that V is equal to a constant into T, or I am going to take T to this side, V by T is equal to a constant. Now, that is again the Charles' law, see. Okay. So, again we have derived, because this equation is reached from the above derivation, in which we have considered P v is equal to 1 by 3 m n u square, which is the kinetic gas equation. So, I have derived Charles' law from kinetic gas equation. Hope it is clear. It is very easy. We will have to reach this equation, take pressure from this side to the right hand side, and keeping pressure constant, all the terms except T is constant on the right hand side, and since pressure is constant, we have V is equal to a constant into T, or I can put it as V by T is a constant, which is the Charles' law. Next is RMS velocity. We know that this is the ideal gas equation. Ideal gas equation is P v is equal to R T. This is the ideal gas equation. Now, we are going to consider the kinetic gas equation for N 0. What is that? Avogadro number. Okay. Now, here I have to put it as N 0, N naught. Okay. This is the Avogadro. Then I can write this equation as P v is equal to 1 by 3 m n naught Avogadro number into u square. Now, comparing these two, this is a kinetic equation. The one I have written, it is for, actually it is meant for n molecules. Now, instead of n molecules, I am taking N 0, that is the Avogadro number of molecules. The equation takes the form like this. Now, comparing these two, I can put R T instead of P v by substituting from ideal gas equation. The equation will be in the form R T equals 1 by 3 m n naught u square. m into n naught. What is m? It is the mass of one molecule. N naught is the Avogadro number. Mass of one molecule multiplied by Avogadro number gives mass of 1 mole, that is m into n naught, mass of 1 mole, or that is equal to the molar mass capital M. I am going to substitute that over here. This is the molar mass. Now, the equation takes the form 1 by 3 m. Oh, sorry, I am going to convert, substitute that. I will get this as capital M u square. Okay. So, this is the molecular mass. Now, I want the RMS velocity, that is the root of square of mean of velocity, that is known as u square. This is the RMS velocity. Okay. So, I have to give the expression in terms of u square equals. U square equals, so I will keep u over here. When I take 3, it goes to the numerator. So, 3, the other side we have R t at the numerator. I am going to take m from the numerator. So, that goes to the denominator, 3 R t by m. Now, I want the root. So, RMS velocity, that is square root of u square, which is equal to square root of 3 R t by capital M. And instead of writing square root of u square, I will just put it as u. U is equal to square root of u square is u. U is equal to square root of 3 R t by m, where u represents the RMS velocity. Hope it is clear. Next, we have to detect the kinetic energy of gas molecules. Again, we are going to take the expression, this is the ideal gas equation, and this is the kinetic gas equation. Okay. Now, this kinetic gas equation again I am going to consider for N0 molecules. N0 molecules means Avogadro number. Okay. So, I can put this as PV is equal to 1 by 3 m N0 u square. Now, what I am going to do is, again as we have done it in the previous case, I am going to substitute for PV as R t from ideal gas equation. So, substituting, that is we are going to substitute PV as R t. So, R t equals 1 by 3 m n naught u square. Okay. Now, here we do not have any kinetic energy term. We know that kinetic energy is equal to half into, for so much molecules I can put it as m n 0 u square, because this is what we are going to consider in this case, that is mass into n 0 number of molecules, which will be the molecular mass. Okay. Now, this is the case when we have 1 by 2, but here we are having 1 by 3. Now, what to do? So, what I am going to do is multiply this equation with 2 in the numerator and 2 in the denominator. So, this will be 2 into 2 by 2 into 1 by 3 into m n 0 u square. Okay. Now, what I am going to do is I am going to take this 3 to this side and I am going to put it as 1 by 2. So, the equation will be 2 by 3, okay, the 3 has come out, 1 by 2, this becomes 1 by 2 into 1 by 2 m n 0 u square. Now, this term, this is the kinetic energy which we can represent it as E k. Okay. So, E k R T equals 2 by 3 E k, sorry, E k, or E k equals, see I am going to take this towards this side. So, this becomes 3 will be in the numerator, 2 in the denominator, you will get E k equals 3 by 2 R T, and this is for 1 mole, because here N 0 stands for Avogadro number and that is for 1 mole. So, we have E k is equal to 3 by 2 R T per mole, and this is an equation, again you will have to remember E k is equal to 3 by 2 R T for 1 mole of any gas. Next, we will go for some problems based on this. The first problem is calculate the total kinetic energy in joules, joules means SI system, of the molecules contained in 22 gram of carbon dioxide at 27 degree Celsius. Now, the problem arises, we do not have number of moles, they have given the mass of carbon dioxide here, but if you get the mass, you can find out its number of moles provided we know the molecular mass. So, molecular mass of carbon dioxide is 44 into 10 to the power minus 3 kilogram per mole. Okay. So, this is a molecular mass of carbon dioxide. So, we know that. Now, here the temperature is given in 27 degrees Celsius, we have to convert that into absolute scale. So, we are going to write the molecular mass of carbon dioxide is equal to 44 into 10 to the power minus 3 kilogram per mole. So, that is I have got that. Then what else do we need? We need the temperature is equal to 27 plus 273, and that will be equal to 7, 10 carry over, it is 300 Kelvin. Okay. Then the value of R, you want that in SI units, it is 8.314 joules per Kelvin per mole. So, all these values we have got, and applying this we will get the expression for kinetic energy for 1 mole. Now, this is the expression for 1 mole, E k is equal to 3 by 2 R T, and one more point, we have got this mass of carbon dioxide, I forgot to put it that is 22 into, it is in gram, minus 3 kilograms. Okay. So, everything is done. Now, we have this expression for kinetic energy is equal to 3 by 2 R T, which is equal to 3 by 2 into R which is 8.314 into temperature, that is 300 Kelvin. Okay. On solving, you will get the answer as 3714.3 joules per mole. So, that is E k. Okay, you got that, and this is for 1 mole. We are asked to find out the number of molecules in 22 gram. In 1 mole we have 6.02 into 10 to the power 23 molecules. Okay, that is 1 mole. So, number of moles we will have to find out. For that, what we do is, we have the mass of carbon dioxide, which is 22 into 10 to the power minus 3 kilogram. Okay. So, mass divided by molecular mass will give you number of moles, that is 22 into 10 to the power minus 3. Okay, divided by so much kilogram divided by 44 into 10 to the power minus 3 kilogram per mole, and you will get the number of moles from that. That is, we know that here it will be equal to 0.5 moles. So, multiplying this value, that is E k, will be equal to, for 1 mole it is 3714.3, that is 1 mole. So, for 0.5 it will be multiplied by 0.5 will give you 3714.3 divided by 2, and the answer will be 1857.15 joules. Hope it is clear, because they are asked to find out the kinetic energy of all the molecules in 22 gram of carbon dioxide. So, we will have to know that how many moles are present in that amount of carbon dioxide. For that, what we did is, we divided the mass by molecular mass, both converted into the same SI units. You get the number of moles as 0.5. For 1 mole, the expression is E k is equal to 3 by 2 R T. We found that for 1 mole, and therefore, for 0.5 mole, that is multiplied by 0.5, or you can divide it by 2, the answer is 1857.15 joules. Now, one more problem. Calculate the average transitional kinetic energy of an ideal gas per molecule per mole at 25 degrees Celsius. What will be the average kinetic energy per molecule? So, you have to find out the average kinetic energy of an ideal gas for 1 mole, and also for 1 molecule what will be the kinetic energy. For 1 mole we have got the expression, and here the only data we get is 25 degrees Celsius, which is equal to 273 plus 25 is 298 Kelvin. So, we are having only the temperature, and that is what we require. So, for 1 mole E k is equal to 3 by 2, and R it is already known, it is 8.314 joules. So, R is known, 3 by 2 into 8.314 into temperature, that is 298 Kelvin. This will be joules per Kelvin per mole, and this will be Kelvin. This divided by Kelvin and Kelvin get cancelled. Then for 1 mole per mole, the answer will be 3716 joules per mole. This is the answer you will get when we calculate this, and this is a value for 1 mole. We are asked to find out both the answers. One is for per mole, the other one is for per molecule, for 1 molecule. Now, we should know what will be the value. We know that 1 mole contains 6.022 into 10 to the power 23 molecules. That means 6.022 into 10 to the power 23 molecules will have a kinetic energy. This is for 1 mole, that is 3716 joules. So many molecules together, they have a kinetic energy 3716 joules. So, for 1 molecule, how much it will come? Just divide it by the number, that is 3716 divided by 6.022 into 10 to the power 23. So, just divide it, that is you divide 3716 by 6.022 and taking 10 to the power minus 23 to the numerator, it becomes 10 to the power minus 23, and dividing you will get the answer as 617.13 into 10 to the power minus 23 joules. That will be the energy for 1 molecule. Hope it is clear, because you should note that 1 mole means it contains 6.022 into 10 to the power 23 molecules, and therefore, this is the energy for 1 mole divided by 6.022 into 10 to the power 23 will give you the kinetic energy for 1 molecule. That is, I can put it as E kinetic per, not mole, it is molecule. Okay. Now, to conclude, in this session we have been seeing deductions from kinetic theory of gases. We derived equations for Boyle's law, that is P V is a constant. We derived Charles' law, in which V by T was found to be a constant. Okay. Then again we have derived an equation for RMS velocity, which is root mean square velocity of a gas, u is equal to square root of 3 RT by m. It is an important equation, you have to by heart it. U is equal to square root of 3 RT by m. Then we derived an expression for kinetic energy of gas molecules, EQ is equal to 3 by 2 RT, and that is for 1 mole. Thank you. That is all.